Welcome to this explainer on the master blueprint for Cambridge-AS and A-level physics. Today, we're totally peeling back the curtain on Syllabus 9702. We want to see exactly how examiners grade your papers, specifically looking at the absolute cornerstone of the whole subject, mastering momentum and Newton's laws. Now, this isn't just going to be some dry textbook reading, okay? This is a highly strategic look at how to actually secure those top marks and topics that pop up in literally every single examination series. Let's get into it.
So we all know the core formulas, right? Force equals mass times acceleration, and linear momentum equals mass times velocity, with force acting as the rate of change of momentum. These core equations, they appear in absolutely every single examination series. But here is the stark reality. Simply memorizing them puts you at severe risk of losing vital grade boundaries, because knowing the equation is honestly maybe 10% of the battle. The other 90% is exactly how you deploy it on the page.
And that brings us to a really painful learner mistake. You know the feeling. Every year, students stride out of the exam hall completely confident they totally nailed the momentum questions just because they remembered F equals ma. But then, results day arrives and they are completely shocked to see they've lost a ton of marks. Why does this happen? Well, it's because they treat physics like a memory test rather than an evidence-based reasoning exercise. Basically, they find evaluating evidence and drawing structured conclusions incredibly hard, completely misunderstanding what the examiner actually wants to see.
This really illustrates the exact academic benchmark you're being measured against. The Cambridge assessment framework absolutely does not reward superficial breadth. Examiners aren't just looking for a dozen loosely related physics facts scattered randomly across the page. Instead, top-performing candidates are rewarded for structured, analytical depth. The graders want to see a connected, conceptual understanding that you can seamlessly transfer to completely unfamiliar contexts. Now, in just a moment, I'm going to show you the exact examiner clue that changes a failing answer completely. But first, you really need the framework that makes that clue obvious. Because think about it, without the structural framework to process the physics, even the most obvious clues hidden in a momentum question will fly right over your head. Okay, so this four-step procedural framework is basically your secret weapon. It turns raw theoretical concepts into the highly specific format those examiners are hunting for. Step 1, identify the concept, like the conservation of linear momentum. Step 2, pull the specific evidence or data directly from the exam prompt. Step 3, apply your scientific reasoning to link the concept to the data. And finally, Step 4, translate all of that into precise examiner wording. Seriously, if you skip any of these steps, your analytical depth just shatters. Now, here is a strategy that can quite literally save your grade. We call it the method mark strategy. In Cambridge physics, you are actually awarded critical points just for showing your process. Let's say you totally mess up the final calculation because you missed a tiny negative sign, which is incredibly frustrating, right? We have all been there. But if your procedural framework clearly shows you applying the principle of conservation of momentum, you still capture those method marks. So, the golden rule: never leave a calculation blank, and please never do the math exclusively in your head. Process over perfection. To actually secure those method marks in practice, your framework has to flawlessly execute 3 specific data interpretation skills. First, you have to systematically extract data from texts and tables. Next, you need to interpret the physical relationships, like, say, how a simple increase in collision time affects the overall rate of change of momentum. And finally, you draw evidence-based conclusions. This isn't just about passing a test, you guys. It's about developing highly professional, real-world scientific skills.
So what does this actually look like on a real exam paper? Well, a flawed answer is usually super vague. It just lists facts without any context, lazily stating something like, "Oh, momentum is conserved." A top-band, specific answer, however, applies the concept directly. It states exactly which masses and velocities interact, and it evaluates the precise parameters of the collision provided in the prompt. That level of specificity is exactly what analytical depth looks like in practice.
To truly wrap our heads around this, we need to go straight to the source. Let's look directly at the principal examiner reports. These are the official, highly authoritative documents where Cambridge outlines exactly where students fell short globally. We're going to zero in on the top 3 warnings regarding why students absolutely hemorrhage marks, specifically on momentum and Newton's laws questions. Okay, so the examiners warn that, first of all, answers are often far too vague. Students fail to provide the specific details required by those higher-order assessment objectives. Second, candidates completely forget strict presentation conventions. They fail to use proper headings, correct terminology, or clear annotations on their diagrams. And third, and this is a big one,
They completely ignore the specific context of the given question, basically writing a generic textbook answer instead of addressing the unique scenario right in front of them.
Let's put this to the test with a quick challenge. Imagine a student writes this. The force increased because the mass accelerated faster, proving Newton's second law. Pause for a second and think about it. Can you spot the critical error here? What is completely missing from this so-called critical analysis?
Well, the missing link is higher-order evaluation. Top-tier critical analysis must always identify limitations, underlying assumptions, and alternative interpretations that directly affect your conclusion. Did the student assume air resistance was negligible? Were there limitations in how the velocity was measured? To access the absolute highest marks in 9702 physics, you have to move way beyond descriptive physics and enter the evaluative level. You must justify your recommendations and clearly outline the assumptions your calculations actually rely on.
Now, when a question asks you to evaluate multiple approaches or data sets, you need a very specific language structure. Think of this as a kind of secret vocabulary hack. Examiners demand that you highlight similarities and differences, supporting each with solid evidence. Using comparative connectives like whereas, conversely, or similarly acts like a giant neon sign to the examiner. It proves you're executing a structured comparative analysis, rather than just describing two things independently. This directly satisfies those higher-order assessment objectives we talked about.
So, you now have the blueprint for turning standard physics knowledge into top-tier exam performance. But as we all know, memory fades quickly without repetition. To really lock these frameworks into your brain, you need consistent exposure, which is exactly what you'll get if you subscribe to the Ace the Exams YouTube channel at acetheexams_IGCSE. Seriously, integrating these high-level strategies requires consistent practice, and that's exactly what we provide over there. All right, so you now have the ultimate high-mark strategy and the structural framework for momentum and Newton's laws. You know to focus on analytical depth, secure those vital method marks, and elevate your answers with critical evaluation. But knowing the system and executing it while the clock is relentlessly ticking down are two very different things. So I leave you with this final, critical thought to ponder. How do you perfectly execute this timed answer writing system before the clock runs out? Join us next time for our next explainer as we crack the code on intense exam time management. See you then.